In this lesson, we're going to look at graphing Limassons and Rose curves, two special kinds of polar curves. Let's start with Limassons. A Limasson is a polar graph with an equation in the form r equals b plus a times sine theta, or r equals b plus a times cosine theta. There are several variations of the shape. Below on the left, we have what's called a looped Limasson. You may wonder about the spelling. There's a little thing that hangs off of the C that's French, and it makes the C have a soft sound, so it's called the Limasson. And then in the middle here, we have a curve that we've talked about before. This is a special type of Limasson that looks like a heart, so we call it a cardioid. And then you may notice there's a little dimple in the bottom of the next curve. We call this a dimpled Limasson. To get an idea of what each of these, how each of these graphs will take and create a table of values. This is not going to be a preferred method, but it's going to be a method by which we can kind of see how the polar curve is generated. So let's create an extra column here for the cosines of each angle theta. Cosine of 0 is 1, of 60 is a half, cosine of 90 is 0, cosine of 120 is negative a half. Remember, as cosine goes, as we go into the second quadrant, cosine becomes negative, then followed by negative 1, and then back up, negative a half, 0, positive a half, and 1. So when cosine of theta is 1, then the radius is 3 plus 2 times 1, or 5. When cosine is a half, the radius is 4. When cosine is 0, the radius is 3. When cosine is negative 1 half, the radius is 2. When cosine is negative 1, the radius is, 1. Let me check my arithmetic there. Not 0, but 3 plus negative 2 is positive 1. And then we're going to head back up from there to a radius of 2, a radius of 3, 4, and finally back up to 5. And I see what the issue here is. I've miscopied those second numbers in each of the computations there. The final computations are correct, but I miswrote those. All right, let's graph those. When we're on 0 degrees, the radius is 5. At 60 degrees, the radius is 4. So we have the graph kind of looking like this, spiraling sort of inward. At 90 degrees, the radius is 3, continuing to move inward. At 120 degrees, the radius is 2. And at 180 degrees, the radius is 1. At 240, the radius is back to 2. You can see that little dimple in the Limasson forming there. Oops. Kind of looks like that. I haven't made it into a very smooth curve there, but you get the picture. And at 270, the radius is 3. At 300, the radius is 4. And then back at 360, the radius is 5. Same place we started when theta was 0. Okay, so that's one of those dimpled Limassons. That's the easier type of curve to generate. And now let's see what happens when we have a looped Limasson. Let's create an extra column for this one for the sines of each of these angles. Sine of 0 is 0, of 30 is a half, sine of 90 is 1. And then in the second quadrant, sine goes back down. Third quadrant becomes negative. And then the fourth quadrant heads back up from positive negative 1 back up to 0. So at 0 degrees, the radius is 2. At 30 degrees, the radius is 4. And at 90 degrees, the radius is 6. At 150, radius back down to 4. And at 180, the radius is back down to 2. Now at 210, the radius is 0. 2 plus -2. And at 270, the radius becomes negative. It's -2 there. At 330, radius is back to 0. And at 360, the radius returns to its original value at 0 degrees of 2. Something to watch out for in this one. From 210 to 330, the radius in between those two values is negative. So I'm going to mark that off between 210 right here and 330 right here. On this interval right here, the radius is going to be negative. So as we graph, let's keep that in mind. All right, so at 0 degrees, we start with a radius of 2. At 30 degrees, the radius increases to 4. And then at 90 degrees, the radius increases to 6. So we can kind of see, as we connect the dots here, what's happening, sort of spiraling outward. Now, in the second quadrant, it's going to spiral back inward. At 150, the radius is 4. And then at 180, the radius is back to 2. This is the easy part of the graph to generate. And then at 210, the radius goes to 0. So I'm just going to kind of mark that off. We're not entering that yellow territory that I highlighted. And then what happens in between 210 and 270? Well, in between 210 and 270, the radius is negative. So I'm going to draw this one with a different color here. Between 210 and 270, the radius goes from 0 to -2. Well, here's, in the dot that I just drew in green, that's a radius of -2 at 270 degrees, which looks like it's on the 90-degree spoke. So what's happening here? The angles are in the third quadrant, but the radius is negative, which means the points are actually showing up in the first quadrant. And then what happens on the next interval between 270 and 330, the radius is negative. Those are fourth quadrant angles. So the graph shows up in the opposite quadrant, quadrant 2. And then between 330 and 360, the radius goes from 0 to +2, back to positive. So you see that creates what we'd call a looped Limasson. All right, let's take a look at this using another method. And I think this method is a little bit faster and easier. It involves graphing a few less points, but it gets us a pretty rough sketch fairly easily. It involves graphing the equation r equals 2 minus 2 times the cosine of theta on the vertical and horizontal axes first. So we're just going to graph it as a regular cosine function. So just some things to keep aware of. What does this 2 do? This moves the graph up 2, which means that our midline is up at y equals 2. And then the negative sign, that's multiplying the cosine of theta, means the graph is flipped upside down. And then finally, that last coefficient there, times 2, that's a vertical stretch. Or it means instead of an amplitude of 1, the cosine has an amplitude equal to 2. All right, so what does that mean? Our midline is up 2, and there's an amplitude of 2, which means that the graph will go 2 units above that value and 2 units below to 0. And the graph is upside down. An upside down cosine starts at its minimum and then heads into the middle, up to the maximum, back to the middle, and then back to the minimum. So it's going to look like this. The angle measures are 0, 90, 180, 270, and 360. All right, now we're just going to transfer that graph onto the polar coordinate system. So just taking a look at each of our points. So we look at that first point right there. That's a radius of 0 with an angle of 0. So that's whenever the radius is 0, the point lies on the pole. All right, let's take a look at our second quadrantal point. By the time we get to 90 degrees, the radius goes up to 2. So that means as the graph rotates through quadrant 1, the radius increases from 0 to 2. Now as we rotate through quadrant 2, between 90 and 180, the radius increases to 4. And then when we hit 270, the radius is back down to 2. And then when we get to 360, the radius returns to 0. And that's one of those cardioids. We can see that the radius is equal to 0 in exactly one place on that graph, at 0 degrees, or after a full revolution, 360 degrees. All right, let's check out another one. R equals -1 plus 5 times the sine of cosine theta. So that -1 means the midline of the graph is down 1. The plus means that it's a right side up sine function. And then lastly, that 5 in front of the sine function means that the amplitude is equal to 5. So now let's graph that. Our midline is down 1, and the amplitude is 5, so that means the graph will go 5 units above -1 and 5 units below -1. This is a right side up sine function, so it's going to start in the middle, go to its maximum, back down to the middle, to a minimum, and then back to the middle. And then our angle measures are 0, 90, 180, 270, and 360. Very rough sketch there. So we start at 0 degrees with a radius of -1. That means that that point's actually going to appear on the 180 degree spoke, the opposite spoke. All right, then what's really important here is this point on the graph where the graph goes through the x-axis. That means that our radius is going from negative to positive, which means graph is passing through the pole. So as we graph, the first part of the graph between 0 and some small angle smaller than 90, the radius is negative. So that means the graph's actually appearing in the opposite quadrant, quadrant 4, and then the graph passes through the pole. And then by the time we get to 90 degrees, the radius has increased to 4. And then rotating through the second quadrant, the graph passes through the pole again, so that when we get to 180 degrees, the radius is -1 again. Then for the rest of the graph, the radius is negative. So between 180 and 270, that would be in the third quadrant, the radius is negative, which means the points are actually going to appear in the first quadrant. So when we get to 270, the radius is -6. That's actually going to appear on a 90-degree spoke. And then in between 270 and 360, the radius is still negative. So that means that the graph's actually appearing in quadrant 2, and our Limasson loops back around on itself. All right, there's one for you to try. Try the next one and pause the video. All right, here is the graph of the looped Limasson. We know that it's going to be looped because the graph of the of r versus theta on the vertical and horizontal axis, the radius goes from negative to positive, so we know that there's some looping going on in the graph. All right, now let's move on to Rose curves. A Rose curve is a polar graph that has an equation in the form r equals a times sine of n times theta, or r equals a times cosine of n times theta. There are several different kinds of Rose curves, and they're just classified by the number of petals. So there are 3 petals in this first one, 4 petals in the second, and it looks like we have a total of 8 petals in that final one on the right. We're going to start out the same way that we did before with a table of values to get an idea of what these look like. So let's make some extra columns here. We need to double the angle, and then we need to take the sine of that double angle before we can get the radius value. So double the angles are 0, 90, 180, 270, 360, 450, 540. You notice we're just going by 90s, right? Because the thetas are going by 45s. So the 2 times thetas are going by 90s. So sine starts at 0, up to 1, back to 0, down to -1, back to 0. Those are just the quadrantal values there. And then repeats that same process, back up to 1, down to 0, down to -1, back up to 0. To get the radii, we just need to multiply each of those values by 4. So 0, 4, 0, -4, 0, 4, 0, -4, and 0. All right, let's graph those. At 0 degrees, the radius is 0. That's at the pole. By the time we rotate to 45 degrees, the radius is 4. I'm going to highlight that wedge there between 0 and 45 degrees. So that means our graph is contained in that highlighted portion. The radius is going from 0 to 4. So the graph is doing something like that, curving around something like that. All right, then between 45 and 90, the radius goes from 4 back down to 0. So that's the portion from 0 to 90. Then from 90 to 135, and let's highlight that portion right there, from 90 to 135. I'll kind of highlight that one in green. There's the 90 to 135 wedge. Between those values, the radii are negative. That means it's appearing in the opposite quadrant. So between 90 and 135, the radius goes from 0 to -4. So it's going to appear in quadrant 4. And then between 135 and 180, the radius goes back down to 0. Now in the next segment, we're between 180 and 270. If you look at the 180 to 270 part of the graph right here, the radius goes from 0 to +4 to 0. So those are third quadrant angles. The graph will actually appear in the third quadrant because the radius is positive. And then for the last portion of this, the angles are quadrant 4 between 270 and 360. So that means if the radius is negative, the graph will appear in the opposite quadrant, quadrant 2. And there we have the final fourth petal of the four-petaled rose curve. Quick thing for you to notice, the 4 in front of the R is the length of each petal. How far out does each petal go? And then that 2 in front of the theta there, the 2 that's multiplying the theta, is determining the number of petals. Notice that there's 4 petals. All right, let's take a look at the next one. 5 times the cosine of 3 theta. We'll create some extra columns here for the table of values. We're going to have to triple each of the theta values and then take their cosines. And then finally multiply by 5 to get the R values. So triple would be 0, 90, 180, 270, 360, 450. Oops, excuse me. Yeah, 450, and then triple 180 is 540. I'm just going by 90s, right? Because we're going by 30s and the thetas. So now next value would be 630. Next value would be 720. And then what's next after that? By 90s, that would be 810, 900, 990, and 1080. Okay, notice the 3 thetas are just quadrantal values. Cosine starts at a maximum of 1, down to 0, down to -1, back up to 0, back up to 1. That's one full cycle. Then repeats. And then repeats again. To get the radii, we just need to multiply each of those values by 5. All right, so at 0 degrees, the radius is 5. And then by the time we get to 30 degrees, the radius is 0. So between 0 and 30 degrees and that wedge, the radius went from 5 down to 0. Now there's the 30 to 60 degree wedge. Well, 30 to 60 degrees is this wedge that I'm highlighting in blue right here. In between 30 and 60, though, the radius is negative. Actually, if you think about it, between 30 and 90, the radius is negative. So that means our graph is going to appear in the opposite quadrant. Between 30 and 90. So at 60 degrees, the radius is -5. And then by the time we get to 90 degrees, the radius is back down to 0. Okay, so now we've graphed all the way from 0 to 90 degrees. And from 90 to 120, the radius is positive again. So at 120, the radius reaches a maximum of 5. And then between 120 and 150, the radius goes back down to 0. Whoops. And then from 150 to 180, the radius is negative. So at 180, the radius is -5. And then our graph looks like it completes there. We could continue graphing, and we didn't notice we didn't get all the way to the end of the cycle. We only made it to 180 degrees in the table of values. If we keep going, we're actually going to trace over the 3 petals once more. So there's really 6 petals. Notice the 3 theta, but the petals graph on top of each other, so we only get a 3-petaled rose curve. So let's generalize that. A rose curve with equation r equals a times sine of n theta, or r equals a times cosine of n theta, has n petals if n is odd, and 2 n petals if n is even. That's one of those things that'll help you make some generalizations to make these easier to graph. All right, let's use our other technique by graphing r versus theta on the vertical and horizontal axes. And we have -5 times cosine of 3 theta. So that means that this is an upside down cosine graph with an amplitude equal to 5, and the period of this one is equal to 360 over 3, or 120 degrees. Okay, so that means there's no shift in the midline. Midline is at the x-axis. That means we're going to have a positive 5 and a negative 5 as the max and min. If the period is 120, that means the halfway point is 60 degrees, and each sort of quadrantal portion of the graph is a length of 30 degrees. So it's an upside down cosine, which means it starts at its minimum, goes up to the maximum in the middle, and then comes back down to the minimum. And so our radius starts at negative 5 when we're at 0 degrees. By the time we get to 30 degrees, the radius goes down to 0. Then between 30 and 60, the radius goes back up to 5. And then between 60 and 90, the radius goes back down to 0. Between 90 and 120, the radius goes to negative 5. So notice we're on the opposite of the 120 degree spoke. Now we're not quite finished, right? So what's going to happen after that? Well, the graph is going to go back to 0 on the next 30 degree interval. And then between 150 and 180, the graph is going to go to positive 5. And then we have all of our 3 petals. All right, let's try another one. R equals 5 times the cosine of 4 times theta. So this will be a right side up with an amplitude of 5 and a period equal to 360 divided by 4, or 90 degrees. So it's going to take 90 degrees to make a full cycle. 45 in the middle. Those would be 22 and a half. I'm not going to worry too much about those. Maximum of 5, minimum of negative 5. And this is a cosine graph, but it's right side up. So we're starting at positive 5, down to 0, down to negative 5, to 0, back up to 5. So at 0 degrees, we have a radius of 5. And then somewhere at 22 and a half degrees, which I'm just going to kind of estimate, here the radius goes to 0. By the time we get to 45 degrees, the radius is negative 5. And so that's in the opposite quadrant. Back to 0. And then by the time we get to 90 degrees, the radius is back up to positive 5. We're not really quite done with our graph here. So let's imagine that we keep going between 90 and 135. The graph is going to go all the way from positive 5 to negative 5. And then between 135 and 180, the graph's going to go from negative 5 back to positive 5. On the next 45 degree interval, the graph's going to go from positive 5 back to negative 5, back to 0, and then back to negative 5. I'm sorry, positive 5, back to 0. And we can see where that empty 45 degree spoke is, and then we finally finish out the graph here. This one's kind of a bear to graph because there are so many petals. Let's think about that though. For theta, there ought to be 8 petals, and we can see that this graph is 8 petaled. This one's a hard one to do by hand for sure. Maybe not such a good test question. All right, below here's one for you to try. R equals 6 times sine of 3 theta. Pause the video while you do this. Okay, here's the graph of the three-petaled rose curve. So notice that the sinusoidal graph that we graphed first, the one on the vertical and horizontal axes here, has each petal kind of carved out. The 30 to 60 degree, or 0 to 60 degree petal is this one. And then here's a negative petal. That one's between 60 and 120, but it's negative, so it's appearing in the opposite quadrant. And then you can see that we would have one more sort of hump of the sine function in order to graph that third petal and complete the graph. All right, now we're going to do the same thing but backwards. We're actually going to write the equation given a polar graph. So we're going to start with that graph and we're going to work backwards onto the vertical and horizontal axes here with r on the vertical and theta on the horizontal. So if I'm graphing points here, when we're at 0 degrees, the radius is 3. And then when we get to 90 degrees, the radius goes down to 1. At 180, back up to 3. And then at 270, the graph has a radius of 5. So that kind of gives us an idea of our max and our min and our middle. Here's our midline right here at 3. And I'm going to mark off the angles here, 0, 90, 180, 270, and 360. So the radius starts out when we're at 0 degrees at 3, down to 1, up to 3, up to 5, and back down to 3. All right, this looks like an upside down sine function. The vertical shift is 3. It's upside down, so minus, and the amplitude is 2 times sine of theta. So there is the equation. This is actually a little bit easier process than graphing, but we had to do the graphing first in order to be able to do this process backwards. All right, let's try B here. It looks like our maximum radius here is 5. And if you look at what happens on this graph as we rotate through quadrant 1, the radius gets smaller, and then you notice that the radius becomes negative. So by the time we get to 180, the radius is negative 1. So it appears that our highest radius that we need is 5. The lowest radius is negative 1. And where are we in the middle here? It looks like when we're at 90 and 270, the radius is positive 2, which is halfway in between those two max and min values. All right, so here's our midline. Marking off the angles, 90, 180, 270, 360. Looks like we start at a radius of 5 when we're at 0 degrees. 90 degrees, we have a radius of 2. At 180, we have a radius of negative 1. 270, the radius is 2. And 360, the radius is 5. So this looks like a cosine function. It has a vertical shift of 2, so we'll start with that. It's right side up, plus. Amplitude is 3, so 3 times the cosine of theta. And there's our equation for that graph. All right, the next one is a rose curve. And so let's check out what's happening with this. It looks like our maximum radius there is 5. And we know in a rose curve, the radius becomes negative at some point, so it goes down to a minimum of negative 5. So let's examine what happens here. The radius goes from 5 down to 0. and then the radius becomes -5 when we hit an angle of 90. And then the radius goes back to 0. And then the radius becomes +5 when we reach 180. All right, so that n value that multiplies theta is 360 divided by the period of this cosine function, which is 180, which means our n value is 2. The equation of this graph is r equals 5 times and the graph we can see, since it starts at a max, is a cosine graph, r times the cosine of 2 theta. Let's do another rose curve. Oh my gosh, let's see. What's this graph doing? We've got a lot of petals here. So it looks like our graph kind of starts here and reaches a maximum. That looks like 15 degrees there. So let me write that a little bit more clearly there. So it looks like our radius goes from 0 to a maximum of 5 once we reach 15 degrees. Then it looks like it goes back down to 0 at 30 degrees. I think we can sort of intuit the rest of this graph from there. That looks like the beginning of a sine function. So that means by 45, the graph should have a radius of -5. And then by the time we get to, what would the next one be, 60, the radius should be back up to 0. Well, that looks like a sine function with an amplitude of 5, right side up, so r equals 5 times the sine of, and our n value is 360 divided by 60, which is 6, so 5 times the sine of 6 theta. Now here's another way that we could have figured out that it was 6 theta, and the other way to figure that out is you can count the number of petals. There are a total of 12 petals in this curve, so we know since when n is even, the number of petals is double the value of n. All right, a couple for you to try. Try this rose curve first. Pause the video while you do that. Here's the equation. It's a 3-petaled rose curve, so we kind of knew n had to be 3. And it's a cosine graph because the radius starts at a maximum. All right, try the next one, which is a looped Limasson. Pause the video while you do this. Here is the equation for this looped Limasson. And that's it for the lesson.